there's more we could say about Lie algebras, but just so that we don't get stuck in at a fixed point, we'll move on. We'll return to the study of current algebras. Okay, so our main motivation for this detour on Lie algebras was that we had gone through one round of discussing current algebras for SU2, but we wanted to do it for general groups. Okay, please.
In the last class, when you were talking about the representation of SUN,
Yes.
Young tableau thing,
Yes.
what was the connection between the representation of why representation of SUN has this connection to Young tableau rather than SP or SUN? Is there?
Yeah. Okay. Good. So you see, consider every representation of SUN can be formed by tensor producting fundamentals. This, is not true of SON because there are spinor representations, but let's forget that. That's not the main point. Okay, there are spinor representations which cannot be formed by tensoring fundamentals, but that's not the main point. The main point is that when we take fundamentals and you tensor product them, the various irreducible representations are obtained just by symmetrization. Okay, symmetry properties don't allow things to mix. In SON, on the other hand, let's say we take two guys and symmetrize. That is not by itself an irreducible representation, because we could also contract the indices. Okay, so if you take two fundamentals of SON, you get antisymmetric, which is nice and it's by itself irreducible, but you get symmetric and scalar. So you see, there's an additional operation in making irreducible representations in the SON, similar statements about SPN, other than just symmetrizing. Okay, this is related to the fact that there is an invariant tensor, namely delta ij, that acts only on fundamentals. Okay, in SUN, the only invariant tensor that acts only on fundamentals is epsilon, and that's accounted for by the structure of the Young tableau. So that's the main difference. However, having said this, in my papers, when I want to refer to a representation of SON, I often draw a Young tableau with the understanding that every symmetric guy is made traceless. So with some, if you're just, the main difference in SON and SUN is the trace. The trace gives you, so if you just by hand say that the thing is traceless, then it's more or less like SUN. Okay? And of course, why couldn't you contract indices in SUN? In SUN you couldn't because a fundamental can only contract with an anti-fundamental. Whereas in SON, fundamental is fundamental. Okay? And that's sort of the main difference, and it's a bit of a technical difference. Well, of course, the other difference, of course, is spinors. That is if you want to do representations including spinors, that's far from Young tableau, because you can't make them out of tensor producting fundamentals. That is, of course, the other difference. Okay, excellent. Okay, so we're now returning to current algebra, but we've grown up. And we are now looking at this being in some arbitrary algebra, arbitrarily algebra. J of Z, Z1, let's say J of Z1, JB of Z2. Now, all the same arguments we had before for SU2, more or less go through in structure. So what we will get is K times the invariant tensor, but we've chosen that to be delta AB, divided by Z1 to the whole thing square. Why square? Because J was dimension 1. Okay, plus FABC JC divided by Z1 2. Okay, where FABC is defined such that JA, JB, just in Lie algebra, JA, JB is equal to, sorry, let's put up. Okay, no, maybe I should put down here, whatever. AB, FABC, JC. Okay, so far so good. This is some straightforward generalization. Now, what else did we have in SU2? You remember from our earlier lectures. What else did we have in SU2? We had various things. First, we had that K was quantized. Okay? By the way, all through, I'm always using the convention that largest root has norm squared 2. Okay? You could work more carefully, and Polchinski in his chapter, whenever he talks about current algebras, is very careful. He distinguishes K from K hat. You know, where square root of the largest root squared, yeah, which in our conventions is 2. So K is equal to K hat. Okay, for us, but if you want to be careful, you can keep track of you know, the norm squared of the. For us, it's always largest root norm squares 2, mod squares 2. Okay, fine. So and the invariant, you know, the inner product is delta IP. Yes.
So when we were doing Lie algebra,
yes.
our algebra was similar, right?
That thing there was just Lie algebra. So we take a Lie algebra, and you take currents, which are Lie algebra valued currents.
Okay, but how is it different from like when we say current algebra?
This is the top line is current algebra. Current algebra is a current which carries internal indices, which are Lie algebra indices. That A there is a Lie algebra index, and it's current because it's a function of Z. Okay, in Lie algebra there was no Z. Okay, excellent. Excellent. Now, we found that K was an integer, so that's something we want to understand. Is it still an integer, and with what quantization, that kind of thing, we want to understand that in general. And we also did this, we understood the Sugawara construction. Okay, we also understood the Sugawara construction for the stress tensor. So we can do this in any order. Okay, first, going from this current algebra to commutation relations is straightforward. Right, how do we do it? We do the usual thing, right? We take J, okay, so what is our expansion? J A of Z is equal to sum over n, J A n divided by Z to the power n plus 1. That's the usual expansion we always make. Okay, and therefore we had J n A is equal to Z to the power n J A of Z 1 by 2 pi I, just by Cauchy's theorem. Okay, so this J A n is given as a contour integral of the current. Okay, and you remember that are the general rules that we developed, which said that suppose I want to compute, if I've got something expressed like this, and I want to compute JAN, JBM. I want to compute this commutator. You remember what our rule was? Our rule was take the OP of those two currents. Okay? Look for a pole. The residue of that pole is the current that appears inside the charge that makes up whatever appears on the right hand side of this. Okay? And the 2 pi i's just go for the ride. Because when we take the residue, there's an extra factor of 2 pi I. So we have 2 pi i's, and what's left over is 1 over 2 pi I squared times 2 pi I because of Cauchy's theorem. So there's a 1 over 2 pi I. So what appears is residue of JA of Z, JB of Z times whatever. Residue of whatever appears here. In this case, Z to the n. And let's call this W, or let's call this W, and W to the power m, residue as n goes to m, integrate 1 by 2 pi, Z goes to W, Z goes to W, integrate 1 by 2 pi I. Right, that was our rule. And you remember how we got it, right, the usual contour tricks and so on. Okay, so let's apply this rule. Okay, so what we have to do is to compute this residue when we have Z to the power n J A Z, W to the power M, J B W. So we use the OP that's up there. So we get Z to the power N, W to the power M. When we get K by Z minus W, the whole thing square. Okay? And plus F A B C J C of W divided by Z minus W. In here there's a delta AB, right. Then what we're supposed to do is to take Z goes to W and take, imagine that Z is going to W and isolate the pole. Now in this situation, this is a double pole, but if we Taylor expand the Z around W, we'll get W to the power N plus N times W to the power N plus N minus 1 plus a Z minus W. The Z minus W will cancel. So this thing is N W to the power M plus N minus 1. That's the, so now I'm writing the residue from this term. Is that clear? Okay. And from here we don't need to do much because it's already a pole. So we just set Z equals W. So plus W to the power N plus M F A B C J C of W. Okay. And then, so what we're supposed to do is take this residue and integrate it 1 by 2 pi I times dW of whatever we had here. So N times W to the power M plus N minus 1 plus W to the power M plus N F A B C J C of W. But what's this term? This is delta M plus N times 2 pi I, but this 2 pi I cancels this 2 pi I. So it's just delta M plus N comma 0. Right? Because Cauchy's theorem tells us that if you've got some funny pole, you get 0, but if you've got a real pole, power 1, you get non-zero. And if you got the real pole, you get 2 pi I. So that cancels that pole. And the other guy is, now we look up there. You see, our definition was that JNA, okay, was that a contour integral with the Z to the power N. So we've got W to the power M plus N. So this thing is equal to plus F A B C J C M plus N. Okay, so we conclude that JMA commutator JNB was equal to N here. N here. Which one?
You write JM first, right?
I wrote JN first. Thank you. NM. Thank you. And this was N. K, NK. You're right. This was K and there's an N here as well, right? Yeah. Okay. Now let's look at, we saw something similar with SU2, but just let's look at it once. First, how come there was an N here? How did we know there had to be something like an N? Could this commutation relation have been there without the N? Exactly. The antisymmetry. Okay. This has a delta AB. That's nice and symmetric. But this commutator is antisymmetric. So M goes to N. It should give you a minus sign, but that nicely occurs because of that N. Okay. This is the thing. You know, this is called, this part is because of the central extension. This part is very straightforward. It's just like Lie algebra, except L0 weights have to add. So on the left-hand side, the L0 weights were N plus M, or maybe you might want to call it minus N plus minus N, whatever. Okay, that has to add up, so you get M plus N. Okay, so it's a very straightforward commutation relation. That is just a rewriting of that OP. Okay, great. So this commutation relation we understand well. Okay.
Manifestation of the current
OP. We just translation of the current OP into commutation. These are completely equivalent things. Okay. Now let us turn to this quantization of K. Okay. Let us turn to this business. Okay. Now, now let's see. In SU2, what we did was the following. First, we recalled that in SU2, if we just took all m and n equals 0, that obeyed just the SU2 algebra. Because in that case, you got 0 here, because m and n was 0, and you got FABCJC 0 here. So the 0 modes of the currents obeyed the ordinary SU2 algebra, but that argument just goes through completely unchanged.
Zero mode currents are the same
Are the charges.
charges of the Lie.
Are the charges of the Lie algebra, so they obey the usual Lie algebra relations. Okay? So just following now what we did with the SU2 algebra, we find that JA0, JB0 is equal to FABC JC0. So we've got the J0s obey the commutation relation of Lie algebra. Okay, but in SU2 we did something else also very clever. You remember there we thought of it like J plus, J minus, and Jz. And then we looked at J minus minus 1, J0 0, and J plus plus 1. So, it sounds incoherent because when I say, let me write it down.
We find a SU2 algebra extends.
We find another one, but in a more non-trivial way. Okay? And what we did there was we took, so the analog of that here was there was J plus 0, J minus 0, and Jz 0.
So I think it's better to write down this current algebra in custom while this.
Hang on. Okay. I'm just reminding you what we did for SU2 first. Okay. Okay. So in that case, what we did was we looked at J plus minus 1, J minus plus 1, and Jz 0.
Jz0 minus k
Minus k by 2, minus k by 2, or in fact, k minus Jz 0. There's some 2's we'll get straight when we work it out. Yeah.
Non-zero modes also have an SU2 sort of.
Just let me write this properly. We looked at J minus plus 1, J plus minus 1, and that's how we did it. Okay, so please go on. Yeah, sorry, non-zero modes. Yeah, this is an SU2 subalgebra we looked at from involving non-zero modes. Now, roughly, we're going to do it precisely now, but roughly how did it work? Roughly we got you see, this was going to behave like this even though it was a minus, because it was an annihilation operator. So acting on primary states, it annihilated the state. So suppose we act on the highest weight in SU2, but the primary state, okay, J minus would not annihilate it because it's the highest weight, so it would lower it. But this guy would annihilate it because it was acting on the primary, because of this label. Okay? And this guy would now cause a descendant. Okay? So the role of minus and plus were interchanged. We're imagining this acting on a highest weight SU2 primary state. The first Lie algebra, the first set, the J plus annihilated it just because it was SU2 highest weight. It was Jz equals J. In the second one, the J minus plus 1 annihilated it. Not because of the J minus, but because of the plus 1. Okay? So that's why we thought of, we worded the algebra in this way instead of putting it, switching these two around and switching the sign, which would also have been in SU2. Okay? And this gave us power. Now, why did this by itself form an SU2? We'll get the factors of 2 right, but roughly because when you take the commutation of this with this, you get 1k here from the central term, and you get a Jz from the FABC. You got the minus because instead of doing j plus j minus, we were doing j minus j plus. Okay? We're going to try to imitate that. And as Pabitra suggested, we're going to imitate it for the SU2 that we formed from any root. Okay? So, you remember that there were these E alphas, and their commutations were E alpha, E minus alpha, just in Lie algebra, was equal to 2 alpha dot h divided by mod alpha square. Okay, this formula we're now really very familiar with. Okay, now each of these objects is promoted to a current algebra. H is promoted to a current, E alpha is promoted to current, E minus alpha is promoted to current. And we just have to write down that relationship there. You know, the relationship for what the commutation relations were, wherever we had this here. We have to write that down in this basis. Okay? So I'm writing it down and you see if you, okay, I'm writing down two relations and you see if you believe them. Let me first write down this guy in alpha beta. Just let me write this guy out for E alpha E minus alpha. So E alpha of M, E minus alpha N. This thing is equal to Kn. That's good. Then we got this delta AB, but delta AB was giving us a norm. You know, for these two, that it's clicking, but the effective norm is 2 by mod alpha squared. Right, because we had chosen our, if you remember, we chosen trace of E alpha, E minus alpha to be 2 by mod alpha squared. Okay, so this delta AB there in that normalization clicks with the 2 by mod alpha squared. Right? Okay, so we get this. Okay, plus now what? N first. Thank you. Nm. Thank you. Okay, Kn 2 by mod alpha square. Okay, plus we produce whatever we got in the commutation relations. But the commutation relation was this. So we get 2 alpha dot h m plus n by mod alpha square. Delta m plus n first. Is this clear? Yes.
Let's say we have some highest weight state.
Yes.
So that will be annihilated by both the first generators in the two sets.
Yes.
But will that acting with these lowering operators will give you two different representations?
Completely different representation, because in the first set it doesn't change the level. All the states in the Lie algebra representation have the same L0. In the second set, you keep increasing L0 because you're acting with the creation operators.
Okay, so that state is like some kind of a primary state.
What is a primary state?
Like which are annihilated by all these
L minus raising operators. Yes. So we're imagining. Oh, I didn't even tell you, but sorry. You remember when we studied SU2, we had this notion of primary operator, which was annihilated by all lowering operators. All operaters with positive n's. Whether you call the lowering, raising is always confusing. But okay. Positives, let's call it creation and annihilation. All annihilation operators. Okay. Okay, excellent. So, so we had this this notion of a primary operator, correspondingly a primary state. It's exactly the same as in SU2, so I haven't repeated it. I should have, but you remember, right? Okay, so now in this case, if we imagine acting on the primary state, which is also a highest weight state in the sense of Lie algebra. Primary because it's annihilated by all annihilation operators, and highest weight because in the 0 sector, it's annihilated by all lowering operators. Okay, all the raising operators, E plus alphas.
J plus 0.
J plus in that case, right? Okay, it's like it had Jz equals J in that context, right? So that was now going to form two different representations, two different Lie algebra representations, one at this level and one going down. The one going down is what's going to give us something interesting. Was that your question?
Yeah, but the structure is not.
We're going to discuss it.
Basically, if that was the J representation, this is the K by 2 minus J.
K by 2 minus J representation, exactly.
That's how the J said.
Exactly. So as Omkar said, we can read off which representation we're working with by looking at the Jz quantum number, by looking at the Jz quantum number of the highest weight state. From the point of view of both algebras, this was the highest weight state because it was annihilated by what we're calling the raising operator. Okay, so as Omkar said, in the case of SU2, we could read off what the second representation was, because it was K by 2 or K, whatever it was, minus J was Jz.
Okay, just to be clear once. Yeah, so this L0 that you have commutes with all the loading operators from the first set.
Yes. Yes.
So changing JC will not change your L0 value.
Yes, exactly.
But in the second, it will change.
It will increase because you're acting with J minus ones, right?
Yeah. And also you have all these other bunch of SU2s also from
Plus minus.
plus minus 2, plus minus 3.
Yes. We had many of them, and as we discussed during that lecture, the conclusions we reached from those were less strong than the conclusions we reached from looking at level 1. Okay, that's why we're only looking at 1. Okay, so they all exist, but everything that you can deduce from those, you can already deduce from 1 and more. Okay, that's why we looked at that. Okay, excellent. Now, we're just going to play the same game here. Okay. So, you remember that now let's look at this. This commutation relation is the same as that of J plus, J minus, and Jz if we identify J plus as E alpha, J minus as E minus alpha, and Jz is equal to alpha dot H by mod alpha square, not 2 alpha dot H, because J plus with J minus gives 2 Jz. So there's no 2 there. Right. So in the same way, the 0 modes of this form an SU2 algebra. So first we've got one SU2 algebra from E alpha 0, E minus alpha 0, and alpha dot H by mod alpha square, H0. This forms an SU2. This is isomorphic to J plus, J minus, and Jz. Clear? Okay. Excellent. Now, we also see, by imitating that construction, what we'll do is take E minus alpha with a plus 1. Okay? So we'll take E minus alpha with plus 1. We'll take E alpha with minus 1. And we'll take, now what? Whatever appears on the right hand side of this algebra, whatever appears on the right hand side of this algebra, but on the right hand side of the algebra, we should look here. Okay, we should look here. So we were taking this guy as E minus alpha with plus 1. So we get K plus 1, and then because it's wherever there's 2 Jz, we don't keep the 2. So K by mod alpha squared okay, minus alpha dot h by mod alpha square. Right, we get minus because it's E plus alpha, E minus alpha gives you alpha dot h. So E minus alpha, E plus alpha gives you minus alpha dot h. H0, yes, thank you. H0, and these also behave like J plus, J minus, and Jz. This clear? Okay, now that we've got this, we imitate once again our SU2 analysis. Once again, when we studied SU2, if you remember, we could have, from the point of view of the second SU2, acted on any of the states of the representation. But we found we got the most tight constraint when we acted on the highest weight. So let's do that again here. Okay, we will act as guided by what Omkar told us. We will first identify the SU2 representation we're getting. Okay, clearly we're getting an SU2 representation that is little j is equal to k by alpha mod alpha. So now suppose we are in a representation labeled by we are in a representation whose highest weight is some h, h naught, let's say. Okay, so let's say that the representation, the highest weight state in that representation had hi is equal to h naught I, let's say. Let's put the naught here. Okay, and we are acting this SU2 on a primary which transforms in this representation of Lie algebra. Is that clear? Okay, so the primary transforms in some representation of Lie algebra. The representation is such that the highest weight has weights h naught I. That clear?
So this highest weight state will be labeled by 2j, right?
2 what?
2jz. One with respect to this.
Oh, yeah, hang on. But this highest weight was not a highest weight in SU2. This highest weight was the highest weight in our algebra. So there are many balls in the air here, so you have to keep, that's why it's confusing. You see, what we had is a representation of the algebra. Let's imagine I'm going to call it SUN. It could be whatever, but let me just call it SUN to distinguish it from SU2. Okay, so we had a primary of SUN. The primary state is some representation of SUN. That representation could be anything, labeled by some Young tableau. And when I say I'm looking at the highest weight state of that, I'm looking at the SUN highest weight. Okay, H naught has n minus 1 different entries, the Cartan elements of SUN. Okay, it's how many columns of length I in the Young tableau, and that's what this H naught is. This clear?
So this state is annihilated by all the E alphas for alpha being positive.
All E alphas for alpha being positive. That's exactly. Though we're not going to use, right, it's true. Yeah, and that fact gives us the most constraints when we look at this funny SU2. We could have looked at any other states for this funny SU2, because all states would be annihilated by the funny SU2. Because it annihilates all states in the SUN representation would be annihilated by funny SU2, just because they are current algebra primaries. Okay? But when we discussed SU2, I don't know if you remember, we went through this discussion. We could have done this with all states in the representation. We got the best constraint from the highest weight. So we're taking that lesson and going forward. Okay? So we're going to act on the state, the highest weight state, namely the state whose HIs are HI0. This clear? Okay? And therefore now we can read off, there are lots of zeros here. Let me not call it 0, just HI. Okay? Therefore, now we can just read off what the value of SU2 is. This j is equal to this minus alpha dot h divided by mod alpha square, where h is the highest weight vector of our SUN representation. Is this clear? Okay? It's the highest weight of this SU2 algebra, of the second SU2 algebra, when acting on the SUN highest weight. Okay, that SUN highest weight, primary SUN highest weight, was a primary for three things. It was primary for the SUN representation at level 0. It was a primary for this SU2 because it was highest weight. Okay, and it was also primary for this SU2 just because it was primary. Clear? We are going to use this SU2 now. Is this clear? Okay, so we have J, little j, the JZ value. I'll call it JZ to be clear. Okay, but let me call it little j because it's a representation label. Little j, what we normally call j, is equal to this quantity. Okay? Now, suppose I have a j equals j state of SU2 and I act 2j plus 1 times on it with a lowering operator.
It should be an
I get 0. Okay? Right? So, what we conclude is that if we act, so E, then now what was the lowering operator? It was this guy, E alpha minus 1. E alpha minus 1 acting, okay, we acting, E alpha minus 1 acting with this 2 into mod k by mod alpha square minus alpha dot h divided by mod alpha square plus 1 acting on this primary state phi, which was highest weight in SUN and primary, is equal to 0. Okay? And this was our basic constraint in SU2. Now let's mine it. But first, is it clear that we get this equation? Okay? Great. Great. So, the first thing we get out of this is the following. Let us first choose this representation to be the trivial one, namely identity. The identity operator. This worked for any primary representation, in particular the identity. Identity is very simple, doesn't transform under SUN. So its H's are just 0. Okay? Okay. So what we found here was that E alpha minus 1 to the power 2 k by mod alpha squared minus alpha dot h, sorry, no alpha, plus 1 on identity is equal to 0. This we will use several times. Now there is something else that we find. Because you see, this k, the difference between j and minus j for an SU2 representation, another way of saying it is that this object always has to be, this object here always has to be a half integer. Okay? So this object here always has to be a half integer because it is a, it has to be a half integer. Okay? Let's take the case where this is identity. Okay? So we conclude that k by mod alpha squared is equal to half integer. SU2. Right, we could have said it another way. We could have taken the highest weight, then the lowest weight, subtracted them. We would have got an integer. Okay? So k by mod alpha squared has to be a half integer. Now, in our convention, this has to be true for all roots. Let's apply it. Let's apply it to the. Okay, let's work first. suppose in an example, there are some algebras where there are two roots whose length square is 2 and 1. Okay, there are some algebras like SUN actually have all roots equal. Simply laced Lie algebras, right? So, so these guys, mod alpha squared was just 2. So for them we get k is 2 times a half integer, which is an integer. Okay? Now, in the case that you had 2 and 1, you get k is from the from the larger roots you get k is an integer. Okay? From the smaller roots you get k is a half integer. You have to take the most stringent condition. So k is an integer. Right? You do it for the larger root, you get that k is an integer, and that in particular obeys the condition for the smaller root. It should work for every root. Okay? And so we conclude that with this normalization, k is equal to integer. From the representation theory perspective. Yeah, we're using unitarity of the SU2 representations. Right. Yeah. Exactly.
So when you were discussing this conversation of level and the SU2 case, you were talking about the Westermann model of the where this flux was okay.
Yes.
And now we are doing some arbitrary group manifold.
Now there's an arbitrary group manifold. There's a very similar kind of thing. It's, when we look at SUN, okay, when we look at SUN, there are SU2 subgroups of SUN, okay, and you can turn on fluxes within each of these SU2 subgroups. It behaves very simple. We'll have a lecture on this, on Wessel-Minowit and Sigma models with arbitrary groups, but hang on for a moment. So Witten's original paper on non-abelian bosonization was for arbitrary groups. Okay, we'll have a lecture on that, but hang on. Okay, excellent. So what we've got is that with our normalization, with our normalization as defined that way, k has to be an integer. Okay, all good? Okay. Next thing, what can we say about allowed highest weight states? You see, this guy was the highest weight of some SU2 representation. Okay? And therefore it had to be that k by mod alpha squared minus alpha dot h by mod alpha squared was greater than or equal to 0. Because every highest weight, every representation of SU2, the highest weight state has positive Jz, positive and non-negative Jz. Okay? And so we conclude that it had better be that all representations that appear in a unitary manner in this theory have alpha dot h less than or equal to k. What was the SU2 analog of this statement? In SU2, we had that J was less than K. The representations were just labeled by K, J, and J was less than or equal to K. Okay, this is what's replacing that. Some highest weight statement. Okay, so it's a very lovely and clear condition. Okay, on allowed representations. Representations that obey this bound are sometimes called integrable representations. Okay, they're called integrable for a reason I'm not totally sure about. It's probably something to do with the Kaczmarek algebra representation theory. From our point of view, they're just unitary. They're representations that obey the unitarity constraint. Mathematicians have some different way of thinking of it. That's why this integrable thing. I don't even know why. Yeah.
So this k being integer comes from when you take the case phi being an identity representation, right?
Mm-hmm.
Does this hold true for other representations?
Yeah.
What can you say about other representations?
Yeah, good. You see, since we got it, acting on one representation, it was always true. But it's a good question. Okay, it's a good question. You could ask: Can we get more information from other representations? Okay, so this is what we just did. So what we got was that this object here, which was the jz value when we acted on an arbitrary representation, this had to be equal to half integer. Okay, so multiply both sides here, we get 2k by mod alpha squared minus 2 alpha dot h by mod alpha squared is equal to integer. But this we independently know is always an integer, because h is an element of the weight lattice. Right? So this here was not changing the integrality properties, because this was an integer. We added to it an integer, or subtracted from it, it remained an integer. So we got nothing new by looking at any other state. It didn't even matter that it was like, the highest weight state. Just any state in the weight lattice would have kept the integrality property. What we are learning is some positivity stuff. And that was the statement. Is this clear? Is this clear? Right? So we get no new integrality information about K acting on an arbitrary state, but we do learn which states can appear. Okay, excellent. So, so we had this thing, and then in SU2 we did two other things. We followed the analysis of Gepner and Witten to demonstrate that all non-integrable representations decoupled from any conformal block containing even one non-integrable representation was just 0. Okay. Same is true here. Let me show you. Okay. So what we're going to start with is E minus 1 alpha to the power, let's act on identity. Maybe I'll do the algebra in general first. Okay, that object there, is clearly an integer, because 2 alpha dot h by alpha squared was an integer, 2k by mod alpha squared was an integer, because k itself was an integer, 2 is an integer, and alpha squared is either was 1 or 2. So that quantity is some integer. Okay, let's call that integer whatever it is p, just so that we don't have to keep writing. So I'll define p is equal to 2 k by mod alpha squared minus alpha dot h by mod alpha squared, and this is E alpha p plus 1 on phi is equal to 0. This was our basic equation. It's a positive integer, exactly. Okay, now what we did was look at a conformal block which had phi and then some O of z, and then some O1, Z1, On, Zn. Okay, and we wanted to work out this equation. E minus 1 alpha to the power p plus 1 on that operator, therefore acting on the operator within the conformal block, is equal to 0. Okay, so we did it one at a time. I'll just remind you how we did it. First, let's just act with one E minus 1 alpha on this. But E minus 1 alpha by that equation, okay, E minus 1 alpha is acting on phi, so we do an integral centered around phi. So, but from that equation we find that E minus 1 is divided by a 1 by z. Okay, 1 by z is around the center for this operation is z. So So let's say E minus 1 alpha on phi O1 Z1 of Z, O1 Z1 On Zn is equal to integral 1 by 2 pi I dw by w minus z. Okay? And then correlation function of what? Then correlation function of what we get when we take E alpha of w, okay, phi of z, and then O1 Z1 On Zn, and this contour is taken so that if this is the point Z, W circles it like this. Is this clear? Okay. Now we did the following. What we did, now we did the following. Okay? We then took this contour and deformed it around the sphere so that it acted on everything else. Okay? So we took this contour and deformed it around the sphere so that it acted on everything else. So we had this guy acting anti-clockwise. This was acting anti-clockwise on this. So it will act clockwise on all the other guys because we're surrounding it from the other side. Okay? So this was equal to sum over clockwise action. So I'll put a minus and then make it anti-clockwise. Minus 1 by 2 pi I, and then the same thing, dw w minus z E alpha of w phi of z O of O1 of Z1 On of Zn, except that now a contour, so suppose this was the point Z1, Z2, sorry, Z, Z1, Z2, Z3, because I put the minus sign, our contour now acts like this, some of these contours. Okay, it doesn't act on Z anymore, just acts on these. Clear?
Phi of z can come out of the integral.
What?
Phi of z is out of the integral.
Phi of z can come out of the integral. Correct. Correct. Actually, the only thing that cannot come out of the integral is w, because the integral is over w. But the important point, as you are indicating, is that by Cauchy's theorem, this integral is only non-zero if we get a pole in the OP. Now, in Z, there was an explicit pole. Okay? But this is a regular term when W approaches Z1 or W approaches Z2. So as far as polology is concerned, this just goes for the ride. In fact, for this part of the contour, we only care about the pole in Z1. Okay? Now we assumed, I even forgot to tell you, but you remember, right, that we have these, the OP between J's and primary operators. Right. Between JA and phi R, JA of Z and phi R of W. You remember that it's R, the representation in the Rth, let's call this zeta, the zeta representation. The representation matrix in the zeta, and this has some representation index. Okay, Ij phi j of W divided by Z minus W. Right? Currents act on states, in primary states and representations. We had this discussion for SU2, same thing, through representation matrices. Okay, in particular, if you do the contour analysis on this and look at how J0 acts on any state, it will transform it in exactly the representation of that state. So the J0 is just the representation matrix is really, Okay, so we had this, this, and we use that here. Okay, so what we do is we use this, the action of E on, let's say, OZ1. Okay, now, so we act our E on OZ1 and we get something like this. Okay, we get this E alpha in the appropriate representation acting with this, with the O, and we get this pole here. We're interested in taking the residue because of Cauchy's theorem. Okay, and so what we get in the end is the following, just E alpha in representation. Okay, so suppose now I need better, I'll just call it 1, representation 1. O1 is in representation 1, O2 is in representation 2. Okay, Ij, okay, so here there should have been representation indices. Yeah, it's such a pain. I1, In, that kind of thing. Okay, now this one will be I1, J1, no, now K1, M1, whatever. Now this, what happens to this W? It gets replaced by Z1 because we're taking the pole. So on the residue, you just, everywhere that's non-singular, you set W equals Z1. Okay, so let me write it so that there's more place. We get E alpha, what was this? E alpha, then there was I1, M, this E alpha 1, I1, M1, then this guy remains phi. Okay, this guy becomes O1 of Z1, but M1. Okay, O2 of Z2, whatever, I2, and so on. And then this came with a Z1 minus Z. And then sum over all of them. And then we do it again.
Acts on the second guy.
Okay, then it could act either on the first or the second. Okay, we do it again. Again, we act with E minus whatever, E minus alpha, this on this, and once again transfer the contours onto the others. Okay, so these E's then act on absolutely anything. Okay, so the net result of this operation, is the following. Let me write it down so that I make sure I get it right. I'm writing it down and then we'll see if we believe it. Sum p factorial divided by L1 factorial, L2 factorial, Ln factorial, E theta R1 to the power L1, theta we called it alpha, E alpha R2 to the power L2, E alpha Rn to the power Ln, divided by Z minus Z1 to the power L1, Z minus Z n to the power Ln, and then there is the sum is sum over Li, such that under the constraint that sum over Li is equal to P. So what was Li? Li was the number of times in this whole thing that you acted on operator 1. L1 was the number of times you acted on 1. L2 is the number of times you acted on 2, and so on. Okay? These various choose factors came because of the number of ways you could do that. Okay? And then you have to act with these matrices on, think of the correlator as now something with, as a column in the tensor product space. Okay? And we act with these E's. E1 acts only on the first guy and is identity on the second and third, and so on. And so this whole thing acting on the correlator was equal to 0. Correlator or conformal block was equal to 0. The sum was all L's. All allowed L's such that sum over L's was P. This is multinomial expansion, exactly. Basically what we had was that this E acted like E1 plus E2 plus E3 up to En. Because it acted first on 1, then on 2, then on 3. So what that was really was in its action, it was like E1 plus E2 up to En, and then the whole thing to the power P. And that the coefficients of that is here.
With these factors also, Z minus.
Yeah. Every time you have an E1, you have a Z minus Z. Z minus Z1. This is Z minus Z2. Yeah, now it's a precise statement. It was really acting just like this. And then we just expanded it out.
And this whole thing is some tensor product.
Yeah, and so what is the matrix indice? You see, now the matrix indices are acting just as on SUN representation indices. Right? And on a tensor product of n of the Hilbert space formed out of n SUN representations. That clear, right? Okay, so we got this equation. We had an SU2 version of this equation, which felt less abstract because there was J plus, there was J minus, there was JZ. We all grow up with that. This is the same thing. Okay, great. Now, the next thing we did, if you just recall what we did when we studied SU2. Okay, the next thing we did when we studied SU2 was to take the case that phi was equal to identity. Specialize to the case where phi was equal to identity. Now, in this case, identity inserted at Z, okay, is identity inserted at Z, but it's independent of Z.
I just left my bottle.
Oh, no problem at all. Okay, so we had identity, but identity isn't inserted at any particular point. Could I insert identity at any point and get the same answer? But the right-hand side had a Z in it. So now this equation has to hold for every value of Z. Okay, so in the case that we had just identity, then this one was just O1 Z1, On Zn. So now this is an equation that has to be obeyed by O1 Z1 up to On Zn.
This is a matrix equation.
It is matrix equation and functional equation, right? Because it has to be obeyed for all, for all free matrix indices, but for all Z, for all Z1, and so on. Okay. Now, there is some contour integration argument you can do. Okay, we can even do that if you want. We can, since this holds for all Z, we can multiply this by Z to the power L1 minus 1. Z minus Z1 to the power L1 minus 1 and integrate around Z1. Okay? That will only pick up the pole at Z equals Z1. So then we get, let me say that more clearly. We could do the following. We could what I want to argue is that the only way that this can be 0 for all z is that each of these coefficients are 0. I'm trying to think of a clever argument, a clever way of making that argument. Meaning that independently that they have to vanish, not just the sum over L1, but independently each term has to vanish. It's basically very clear because there's an infinite number of equations here. Because it has to work for all z. You can take it for one z, Taylor expand, blah, blah, blah. There's probably some clever way of doing some contour integrals to exactly isolate on any particular L1 to Ln. There's probably some clever way. I'll leave you to think about it. I feel I should be able to think of it on the spot, but I'm not getting it. So anyway, the conclusion is that this quantity here just has to vanish term by term. Okay. So, so we get E alpha R1 to the power L1, E alpha R2 to the power L2. E alpha Rn to the power Ln on this correlation function for any values of L just have to vanish. Now, this has some, this here, okay, this is an equation in representation space. Right, we're in this tensor product of representations. We've got this expression.
So you isolated the functional part.
Yeah, the functional part basically because there was that free z, each coefficient had to vanish. So then the functional,
This upper
just the upper part had to vanish.
numerator.
The numerator had to vanish, exactly. Okay, what do we conclude from here? Okay. Now let us see. Now let us see what was our conclusion from this. Okay. No. Wait. This is in general not 3-point function. I want to show that the non-integrable that if I've got a non-integrable insertion here, this will always vanish. Just that the coefficient has to vanish. Give me 1 second. Give me 1 second. Let me see what. I know what. Sorry. In fact, for this now we can actually do the argument. Okay, let us suppose, now remember we're looking at identity. So P here, this P was equal to, the total number of times we had to act that thing was equal to K plus 1. The total number of actions was K plus 1. Okay? So the maximum number of times we could act any expression, the maximum number of times we could act any E alpha on any one object, namely the maximum value of L1 was K plus 1. So suppose I wanted to isolate out the term that was L1 is equal to K plus 1 and all others L's equals 0. Okay, that I can do very simply, actually. I don't even need to say it has to be. I can do that very simply just by multiplying this by z minus zr to the power L1 and doing the contour integral. Because that term had only z dependence from this z minus z1, everything else was 0. You do the contour integral, you isolate that out. Okay? And therefore, we in particular find that instead of this complicated expression, we get e r1 to the power k plus 1 on this correlator is equal to 0. Now, what does this mean? Okay, you remember that if we had any integrable representation, okay, that if we had any one of those integrable representations that we talked about before, such that the alpha dot h was less than k, okay, then E alpha on that operator to the power p, where p was k minus alpha dot h plus 1, so a number less than k plus 1. E alpha on that thing to a number less than k plus 1 was always 0. Is this clear? Let me say that again.
Why e is equal to k plus 1?
Because we chose to act on the identity operator. You remember? We had that formula which told us how many times we had to act on to get 0.
Yeah.
And for the identity operator, the value of j was k minus alpha dot h. 2k plus 1. Was it 2k plus 1? Oh, maybe there was a half. Let me. Yeah, maybe it was 2k plus 1. Let me look. We have it up here. There, it was that p plus 1, where p was mod alpha square was 2. Right? So, so it was k plus 1 when it was identity operator, but k minus alpha dot h plus 1 when it was some other operator. And alpha dot h was always positive. So this p that we have to add, so that e alpha minus 1 to the power k plus 1 was always 0.
Will definitely vanish.
Is always 0 for every integrable representation. So this equation here, the one that I just written down, is a non-equation if our insertion was an integrable in an integrable representation. The people there are looking a little anxious. We'll have probably soon leave. Okay, this is clear. However, if the representation was not integrable, suppose we said we don't care about unitarity. Okay, we don't care about unitarity. We're going to add an alpha dot h. Okay, that does not lie in this integrable bound. In that case, there's no null state for this representation. Okay, so this E alpha minus 1 to the power k plus 1, in fact, all E alpha minus 1 to the power anything is just non-zero for this representation. Sorry. Hello, was it okay?
Yes, just that, yeah.
Oh, excellent. I'm teaching, I'll call you later.
Okay.
Okay, see you. Okay, excellent. Right? So in the case that the representation was not integrable, this quantity is not 0. So the only way this equation can be obeyed is the coefficient of this particular, of this object is 0. So we conclude that every conformal block, including one or more non-integrable representations, insertions of one or more non-integrable representations, and every number of integrable, any number of integrable representations vanishes.
But why are we interested in non-integrable?
Maybe you should say we should not be. But it's quite amazing, right? Suppose you weren't interested in unitarity for a moment. Okay, maybe some of our reasoning has used unitarity. But what I mean is this, that suppose somebody were to come and say, look, my, maybe you can think of it as a re-derivation of something we already knew. But let me just say, but it's quite a remarkable thing, I find. You know, suppose somebody were to come and say that he has primary operators in these other representations. Okay, these non-integrable representations. That would be an empty statement, because the correlator of that operator with anything else is just 0. It's like a null state. Okay, maybe if in using these arguments, we've used unitarity of the SU2 and so on, so we have to disentangle where we used unitarity. So maybe you say we have used unitarity, maybe this is just a reaffirmation of the same thing. We have seen from another point of view that these operators are non-operators. The only operators in the theory are those that obey this integrability constraint. Okay? Now I want you to just focus on how remarkable that is. If our theory was invariant under Lie algebra, okay, our theory was invariant under Lie algebra, the total number of possible representations that we could have had were infinite. We've got this current algebra, it has this integer k, and we've just concluded that the total number of representations we can have is finite. Right? Because alpha dot h divided by mod alpha squared has to be less than k. There's only a finite number of representations that gives you like a sphere in this weight lattice. Okay? So it's quite a remarkable statement. The statement for SU2, in the case of SU2, that was j could not exceed k. Okay? And this is the general Lie algebra generalization of that. Okay? In the case of SUN, when we work this out, it turns out to be the following statement. The length of the first row of the Young tableau, okay, the length of the first row of the Young tableau cannot be larger than 2k. It's less than equal to 2k.
So level is the maximal amount of the integrable representation.
Maximum amount of integrable representation. And then that already tells you you've got a finite number of representations, because all rows are smaller than or equal to the first row. Okay, all good? Okay, excellent.
Can this also help us to determine the correlation?
Yes, it can. Yes, it can. In fact, we're going to go through an example now. I'll take 5 minutes extra if nobody's coming to throw us out. Okay. So let's go on to Rajat's question. Can we determine correlation functions? So let's start with 3-point functions. Okay. Let's start with 3-point functions. We do this whole analysis now with phi O1 Z1 of Z, phi O1 Z1, phi O2 Z2. Okay, so that we're going to constrain the correlation function phi OO, phi O1 O2. Okay, and what do we get out of that? Well, we wrote down what we got. Where was it? Okay, we wrote down what we got. We got this equation, but with that phi still there. Okay, so we have phi of Z, O1 of Z1, O2 of Z2, and then we have 1 over Z minus Z1 to the power L1, Z minus Z2 to the power L2, sum all these factors, P factorial, L1 factorial, L2 factorial. In this case, it's sort of simple, right? So let's say P minus L1 and L1, factorial L1 factorial. because there were just two L's. Sum over L1, 1, and then there's E1 alpha to the power L1, E2 alpha to the power L2. This was equal to 0. What? L2 is P minus L1. Yes, L2 is L1. Great. This is the equation we got. Now we will choose phi itself to be an operator, one of the primary operators in some representation R3. Okay? Now, what was P? P was equal to 2 into k by mod alpha square minus alpha dot p divided by mod alpha square, alpha dot h. This is h phi now. Okay. Highest weight of the representation phi. Divided by mod alpha square. Okay. And we had this, sorry, I said p, but this is probably p plus 1. Oh, okay, let's put a plus 1 here. P is this. Yeah, we said p plus 1, so I have just transferred. Okay. So this is the condition we've got. Now, for general correlation functions, when you've got things like this with these z dependencies, since you don't really know what the z dependence of the correlator is, it's hard to disentangle, though it can be done, the z paths from the correlator and the z path from the insertions. But for 3-point functions, we don't have that problem, because we know exactly what the form of the 3-point function is in terms of the scaling dimensions of the operators. And in fact, we know what the scaling dimensions of these operators are by the Sugawara construction, which I haven't yet gone through, but you remember from SU2. Right, the Sugawara construction will relate the scaling dimensions of these operators in terms of their representation. So all the scaling dimensions are just completely known. I mean, the z dependence is completely known. So this equation has to hold for all z1 and z2 with some prefactor, which is just some group indices, times some given z1, z2 dependence. And once again, using some contour or something, you will be able to argue that the only way this can work is if all coefficients vanish. We can't argue so easily for 4-point function onwards, because we don't know the z dependence a priori of the correlator. Though, by choosing an appropriate basis in the space of blocks, you can also argue that. It takes more work. Okay? But here, it's very, very simple. Right? Because z dependence is known.
Z dependence becomes a power of the scaling.
Exactly.
And this coefficient comes out of the
Out of the whole thing.
Out of the stuff, and the whole thing is not trivial, so this coefficient should be.
So what we conclude is that E alpha, E1 to the power L1, E2 to the power P minus L1, alpha on phi, phi O1, phi of z. Now the z dependence are not mattering, it's just the group theory structure. So I will omit the z dependence. Phi O1, O2 is equal to 0. Okay, this is now just an equation on the group theory structure. Now what do we know about the group theory structure? The group theory structure of a 3-point function has to be proportional to a Clebsch-Gordan coefficient, because by zero mode invariance, it's in particular invariant under Lie algebra transformations, and therefore is a singlet under Lie algebra. So it's a way of taking 3 representations and combining them into singlet, which is otherwise known as a Clebsch-Gordan coefficient. Sometimes we call Clebsch-Gordan coefficient taking 2 and getting a third, but that's same as taking 3 and getting singlet, because then you fuse with the complex conjugate of that representation. Vigna 3j symbol. There you go. Vigna 3j symbol. Okay. So it's a way of combining representations into singlet. Excellent. So this is just some structure determined by group theory. And either this thing is 0 or it's not. If it's 0, well, it's 0. If it's not 0, then the coefficient of this structure has to be 0. Okay, that's the logic. Now, let's check when it's 0 or not. Exactly.
By coefficient, do you mean like when you do this tensor product, you'll have all these different coefficients with different values of j's, and that coefficient has to be 0, or?
Yeah. So let's take 3 guys. Okay, 3 representations. There are some number of ways in which they can combine into singlets. In the case of SU2, that's always either 0 or 1. J1, J2, J3 can combine into singlets. One way if they obey the triangle inequality, and 0 ways other ways. But in higher groups, there are often many ways of 2 representations producing a third, and therefore many ways of 2 representations combining into a third. Okay, we could look at some examples, but this is generic. Okay, so what this guy is coefficient 1 times way 1 plus coefficient 2 times way 2 plus coefficient 3 times way 3. So the set of non-zero 3-point functions, non-zero with ways of combining 3 representations into a singlet is a vector space. It has a certain dimensionality. Okay, we choose some basis in that vector space, put coefficients behind it, and that gives us the most general form that could have appeared here. Now, all those for which this E alpha on our basis vectors are non-vanishing. We have to choose them so that no linear combination can change this. But all those such that they're non-vanishing, those guys, those coefficients will have to be 0. So if there exists such objects, okay, if there exist such objects, then we would conclude that instead of this 3-point function being expanded in all possible Lie algebra invariants, we only expanded them in a subset of all possible Lie algebra invariants, those for which this equation was automatic. Right? So the subspace of the space of 3-point couplings such that this is equal to 0 is a linear vector subspace of the space of 3-point couplings, and that is a subspace that can appear in correlation functions. Now let's try to understand this condition. Can it be that there are some for which this guy is violated? Jana? Okay. So let's see, can it be that there are some for which this guy is violated? Let's try to understand how that can happen. You see, what this 3-point function is a way of coupling 3 states to get singlet. Now, let's define this notion, the depth of a state in a representation. Okay. The depth of a state under the root alpha in a representation is the number of times we have to act with raising operator in alpha before we get 0. Every state, if we act enough times with the raising operator, we'll get 0. Okay? So given any state, the number of times you have to act with E alpha so that it's 0, I'll call that D. What? For phi, this depth in that sense, because we acted with the highest weight on phi, the depth would be 1. Or depending on whether we're saying number to get 0 or number to get. So the depths of the other two things are non-trivial. But phi is the highest weight state. Okay, so we have to give a clear definition. Let's say depth is equal to number before you get 0. And let me choose Witten's definition because whether it's number you get 0, let me see. So that there's no confusion. Let us define the depth of a state in R1 to be the largest value of L1 for which it does not vanish. So that's your definition. Depth is equal to largest value of L1 such that E alpha to the power L1 on psi not equal to 0. Okay, so that for P the depth will be 0, as Rajan. For phi the depth will be 0. Okay, is this clear? Okay, good. Now, suppose we had the depth of this, suppose the Clebsch-Gordon coefficients were such that they coupled states whose sums of depth was greater than P. You see this L1 plus L2 runs up to P. So suppose every term in this Clebsch-Gordon coefficient was such that the sums of depth was less than P. Then every such state would be annihilated. Because we act with E alpha to the power L1, E alpha to the power L2. Now, suppose the depth of the first plus depth of the second was less than P, then at least one of these would have to be acted on by more than its depth in order that L1 plus L2 add up to P. Right? So if we have a Clebsch-Gordon, if we have a CG, a Clebsch-Gordon coefficient such that sums of depths, I'm only talking about sums in O1 and O2. Sums of depth is less than P. Then at least one of them would have, one of L1 or L2 or both would have to be more than the depth of that particle, that object, because the maximum otherwise would be depth plus depth, but that's less than P, and the L1 and L2 add up to P. Okay, then these are allowed. See, these are allowed. Meaning this, such Clebsch-Gordon coefficients obey the condition that this thing is equal to 0, their coefficients don't have to vanish.
Are you saying that this whole thing, the depth of this whole thing, E1, alpha, L1, this whole thing has to be less than P?
Yeah, this whole thing is a coupling of three states. A state from phi, a state from this representation, state from this representation, state from this representation. Okay? Now, if the depth in O1, O2 of every state that appears in that sum is less than P,
then that will contribute.
then that is allowed. It's not ruled out. Okay? On the other hand, even if this was not the case, if the depth was the sums of, there was one state in that sum such that the sum of depth was equal to or greater than P, then there would be one term there that acting on that state would not be 0. Okay, suppose the sums of depths was either equal to P. There was even one state in this Klebsch-Gordon thing. It's a sum over many ways of coupling together states. Right? Oh, sorry. I'll half a minute.
Oh,
Sorry. Yeah, sorry, we should stop. But suppose there was even one state that had sums of depth equal to or greater than P, then we choose those values of L's to isolate out that state. And then this thing acting on that is non-zero. And therefore the coefficient must vanish. Okay, so you break up this linear vector space of 3-point couplings, Klebsch-Gordons, into the part that obeys this condition and the part that does not. The precise statement is that the space of ones that obey are the spaces where no states in this coupling have sum of depth greater than or equal to P.
Greater than was not possible anyway, because
What? How could we make singlets? Why not?
because let's say the weight of sum of data
Yes.
is n,
Yes.
and if the weight of phi is smaller than n,
Yes. Wait. Remember that P is K minus alpha dot J, alpha dot H. Please go on.
k minus alpha dot. So,
Oh, 2. Yeah. Please go on. Yeah. Plus 1.
so this is the weight of phi, right?
Is you see the depth was how far below the highest weight you are.
Oh yeah, so
And it's true that the Cartans have to add up to 0 is what you're saying, I think. But that doesn't constrain it. Just when we do SU2, for instance, you can easily work this out and see that there are many things that are ruled out. Okay, I think we should go because Jyotish will leave the room. Okay, as an exercise, I'll ask you to work out this condition for SU2. Work this condition out for SU2 and see what it gives you. Okay.